Thank you. Thanks, everyone. So our first keynote speaker, Professor Stefania Serafin. Stefania is professor of sonic interaction design at Aalborg University in Copenhagen and the leader of Multisensory Experience Lab together with Rolf Nodal. She is the president of Sound and Music Computing Association, project leader of the Nordic Sound and Music Computing Network, and lead of the Sound and Music Computing Master at Aalborg University. Stefania received her PhD entitled The Sound of Friction, Computer Models, Playability and Musical Application from Stanford University in 2004, supervised by Professor Julian Smith III. And her papers on sonic interaction design, sound for virtual and augmented reality with applications in health and culture can be found on her website. So thank you, Stefania. Over to you.
Thank you. Thank you very much, Jung and Frank, to invite me here. It's really a pleasure for me to be here. I will tell you about how I ended up doing what I'm doing now, and also some of the technologies that we developed over the years in our lab, and how we apply them. And I will end the talk discussing some of the current challenges that we encounter when using immersive and spatial audio in different interactive applications. So first of all, how did I end up working with audio? When I was a child, I was playing the violin, but it was more forced by my parents. I always wanted to break the violin. And at the same time, then when college time came, so I wanted to study. I was more technically inclined. I'm not really an artist, unfortunately. I wish I was, but I'm not an artist. So I was working computer science, studying computer science, and also at the same time still playing the violin at the local conservatory in Venice. And after graduating, I wanted to combine these two fields. And totally by chance, I found out about this place, which of course is very famous, IRCAM in Paris, where it is possible to combine music technologies with the artistic application. And I studied there for my master's degree. While there, I figured out that something called physical models existed. And then that's why I got in touch with Professor Julius Smith III, that those of you who work with signal processing know him from Stanford University. Maybe I just remove this because it's so annoying on this clicker. I think I'm loud enough, am I? Yeah. Okay, yeah, because it was clicking a little bit too much. So, and for that reason, then I moved to Stanford, where I got my PhD back in 2003. And until then, I didn't do any work on spatial audio, although many of you might know John Channing, right, who wrote one of the first influential papers on spatial audio back in the 70s. So imagine which kind of technology he had available. But some of his ideas in how to combine technology and perception, they're really very relevant also nowadays, and I can see they're very relevant at this conference. So then in 2003, I ended up in Denmark. So now we are moving a little bit more faster with the years. And in Denmark, what happened is that Nokia, as some of you here from Finland know, had a very big audio lab. But then, unfortunately for them, unfortunately for us, they had to close in 2012. So we could take over their lab. That gave us very nice facilities. And we created what we call the Multisensory Experience Lab. So we call it multisensory experience because although many of us specialized in audio, we are very interested in understanding how the different modalities interact and how can we help individuals which are lacking certain modalities like audition or vision using other modalities like touch, audio, and vision, and understand both how to develop technologies but also how to understand the human experience of using these technologies. So today I will present you two types of research. We will not talk about cultural applications, but I will show you some technologies we have developed and then how we have applied them in different kind of projects. So I started, as I said, in Aalborg back in 2003. So the Aalborg University, for those of you who don't know, is based in the city of Aalborg, in the north of Denmark. We are in Copenhagen. But back in 2003, in the city of Aalborg, they had some amazing virtual reality facility. That is when virtual reality was really not known at all, and it was extremely expensive. That's why they had to close them. So they had a cave, but it required really a lot of maintenance. And look at that horrible virtual reality display. It costed about, like, I would say, 200,000 euros. And it was much clumsy, very bad visual quality, and also expensive. And also the tracking was not as efficient and precise as we find nowadays. Nonetheless, we were involved in one of this. I think this is my first project on immersive and interactive surround sound. So this project was called Benogo, which is being there without going. So nowadays we talk a lot about the sense of presence in virtual reality. What is presence? What is immersion? How can we define them? It's really a topic that we could use, not just a conference, like a lifetime discussing those topics. Anyway, this project was about capturing videos of spaces, physical spaces, and reproducing them in virtual reality. Stupid, right? Now everybody knows how to do them very easily. 20 years ago, the technology was not there. Moreover, the spaces were very static. They were captured with the camera connection of different cameras, but you could not walk in them. You could not hear the sounds. As you know very well, sound is an important element of spaces. So that was our contribution to this project, creating an interactive sonic environment where you could hear your footsteps, you could hear the soundscape, you could move in the space and change the characteristics of the sound like it is in real places. So the idea was technology and user experience of being in virtual places as if they were real. So nowadays we can do that. There are still some challenges. If you think about now navigating, and so we can capture a space with a 360 camera very easily. We can create a soundscape, but still navigating in the space is not completely solved yet. Anyway, now I jump 20 years. So now, 20 years later, as you know, virtual reality is very commercialized and available to a larger audience, and you can easily take it at home. So how do we use these technologies? And I will talk mostly about spatial audio for virtual reality and augmented reality, because that is what we work mostly, and also because, as I mentioned, we are very interested in these multisensory experiences. So many of the applications you will see, they will not only include audio, they will also include vision, movement, and haptics. And that has also, as you will see, some consequences on how to design the audio. So let's start with some technologies. So 5 years ago, we wrote a paper about what are the different spatial elements that are needed in order to create a realistic spatial environment for virtual and augmented reality. So this gives a bit more of a representation of what all the different elements. As you know, and also looking at the proceedings, many of the papers handle precisely the technological aspects. So how to improve HRTF, still that is a big topic. Spatial, reverb algorithm, and how to use machine learning to improve these technological solutions, and so on. So, of course, the big topic, somehow, even after all these years, still there are questions regarding HRTF, right? So many papers, at least, they are here regarding this topic. So I will tell you a project we did and you will see why I'm discussing this project. So as you know, everybody here knows the HRTF, right? This is not an audience that needs an explanation. So, and as you know, in the past, they were captured with a dummy head, and the problem is that we don't all look like this. So the HRTF might work for a specific profile, but it doesn't work for everybody. So a couple of years ago, we had a postdoctoral researcher called Simone Spagnol, supported by the Marie Curie postdoc program. And his project was specifically about understanding how to capture personalized HRTF and also how to expand them using machine learning. So he created what is called the Viking dataset because he recorded HRTF of specific model here in Iceland. So that's why Viking, because they are Icelandic ears. So what this database is available, I will show you where. But one of the applications of this database was to see, is it any useful? So since the group was all boys, they made a shooting game. So in the shooting game, they were investigating how does HRTF personalized help precision on shooting in a horizontal and vertical plane. So these are some of the results. So blue is a completely non-binaural sound. Orange is using a generic HRTF, while green is using an individualized. And it seems that the individualized is really useful, right? There is less horizontal error, there is less vertical error, and also you take less to shoot. Nice, very nice. And also, but in general, after some comments, it also shows that non-expert players were benefiting more for this non-individualized HRTF. And this is still maybe unclear why. But also, of course, it's a very specific application. As I said, the database is available. But this brings one of the points about usability of accessibility, because many of us as researchers, we put this technology available, but then it's almost impossible to find, almost impossible to use, and then nobody or very few, just you and your friends use them. So this is something that I think we could do better, is making our technology more accessible to a larger audience. For example, someone who is doing this very well is Apple. If you have the new Apple iPhone, you can get your personalized HRTF. It's very, very user-friendly. Even my dad can do it. I don't know what he can use his personalized HRTF for, but you can look at your ear, you can capture it, and then both universities and companies, they use this approach now of looking at an image of the ear in 3D, and then from that gather the personalized HRTF. So this is to bring up the issue of usability and user experience of this technology. Another important issue is, do we really need this accurate simulation? So Agnieszka and Paul, in their book, Immersive Audio, that I'm sure all of you know, Immersive Sound, the Art and Science of Binaural and Multichannel Audio. If you don't know it, you should check it out. They have this very interesting graph which shows, there is, of course, a trade-off between complexity and accuracy. So obviously, when you have just a generalized HRTF, it's very easy to obtain, but maybe it's not very accurate. On the other end of the spectrum, you have your individualized measure HRTF that it takes a lot of time to record, but of course the accuracy is also higher. There is an interesting paper that might make us think. It is, of course, not from the audio community. It is more from the human-computer interaction and HCI community, where they say that generalized HRTF might be good enough. So this paper was testing the effect of localization with generalized HRTF in a virtual reality environment. What is very important here is the visual component. So as you know, our brain is plastic. So our brain adapts to different stimuli and improves according to the stimuli that we provide. So how many of you know about the ventriloquism effect? Yes, half of the audience. Those of you who don't know, the ventriloquism effect comes from, you know, the ventriloquist, that puppet, so you have a puppet and you have a voice, and it looks like the puppet is moving the mouth, so it looks like the voice is coming from the puppet, briefly. And it's used a lot also in cinemas, so there is what is called the visual capture, because we have a better resolution, spatial resolution, using visual than audition. So usually if there is a discrepancy between what we see and what we hear, the image will kind of win. And this is the same that was happening in this experiment. Even if the HRTF was not as precise, our brain, when there was a visual image associated to the sound, then our brain was adapting and learning where that object was. This didn't happen when we have only auditory stimuli. So it's very different when we have audio-visual combination in VR and when we have only visual stimuli. So multimodality is a very important aspect. And a side note, I saw that a month ago, Meta released, speaking of usability, this is actually a very usable toolkit, and they released this universal HRTF. So I didn't test this, but what I found it interesting is that they said it is still a generalized, but it has been trained in a way that it works better than usual generalized. So they call it universal, maybe something worth trying and see if it improves. So we talked enough about HRTF, and other elements of this technological setup is also, of course, the space, the reverberation. And another aspect where we can say that we can use, if we have visual cues, we can use them, is in perceiving distance. Like we are much better with our eyes to perceive, localize where an object is, we are also much better with our eyes and see how distant an object is. So if we are making an audiovisual simulation, also in this case, maybe the distance simulation or the reverberation doesn't need to be completely physically accurate, especially if we want it to be efficient, because then our eyes can help. So I would like to show you now some applications, and these applications are in what is called the reality-virtuality continuum. So this continuum was introduced back in '94, and it shows basically how we can go from a real environment to augmented reality, augmented virtuality, and virtual environment. So I will show you some examples in virtual environment and others in augmented reality. So one of the topics that we have been addressing in the last couple of years is working with individuals with the hearing impairment, because we got contacted by the local hospital where they created a new center for hearing and balance, where there are many audiologists that are interested in using more modern technologies to train and test their patients who are from children to elderly. So as you know, one of the new uses, no, not really new, but one of the more recent uses of commercialized virtual reality in hearing research is to help cope with the issues of traditional testing methodology. So traditional testing methodologies are made in a booth where you have only the sound, and of course they lack what is called ecological validity. So a person might say he or she hears very well in a booth, then they go in the real world, then we have all sorts of issues, and then they don't hear. So how can we balance between creating an environment which is controllable, but also at the same time which is closer to real life? And virtual reality is one solution to do that. So also at the hospital, they built a spatial audio system. So the idea is to have a space which looks not like a lab, looks more like a clinic, but also has the capability of a high-quality surround sound speaker system that we have in a lab. One of the problems, though, is that it is very hard to take people from the real world who are very busy to come to a lab, I mean, to an hospital, but also to use their time also to be part of experiment. So this is why also most of the experiments that I see also in the proceedings here, it is much easier, it's much more convenient to use our friends, let's say the subjects that are from the university or from the company and so on. But of course, then we lose in diversity. So there is also this balance. And one of the first experiments, again, that we did in the lab regarding virtual reality for hearing, it was in our anechoic room. Again, thank you, Nokia. So in the anechoic room, we had 8 speakers. So the idea was to understand, can we use virtual reality to prototype new hearing aids? So hearing aids now, they are becoming really much more powerful. So you can also zoom in not completely, it doesn't work completely yet. Of course, noise environments are still a challenge. But the idea is, would it be possible to, if you have a conversation like the classic cocktail party or a dinner conversation, would it be possible to zoom in some specific speakers? And also, sorry, how do you zoom? Do you want to zoom with your eyes? And now you can do that in virtual reality because you have eye tracking embedded. Here we were using the Vive device, so it's a couple of years ago. Now many more devices have eye tracking embedded. So you can look at the speaker and you can zoom on this specific speaker, or you can point with the joystick. So the idea was to understand, first of all, does it work? Can people recognize a specific listener in a conversation? And also, which interaction is the best? So we didn't have a really conclusive result, but we saw that it is a good way to prototype hearing aids or complex listening scenarios. So last year, or 2 years ago, we also started working again with the Center for Hearing and Balance and with children. So we had these very nice collaborators. They are all audiologists, so they really care about the children and help them. And one of the issues that children or individuals in general with hearing impairment have is sound localization. That is really a big challenge, especially because, now I'm talking about children, but in general, there are different kinds of hearing impairment. Some, they have one, let's say, good ear, and the other is completely damaged, or they have a cochlear implant. So there are all different kinds of, and do we know how these people recognize spatial sound, where the sound is coming from? Not really. And also, how can we help them to improve their, what is called their spatial awareness? That was the goal of the project. So to use virtual reality training through gamified virtual reality experiences to train their spatial awareness and help them, here we are talking about children, so help them in situations where they have difficulties, and the situations where they have most difficulties is in playgrounds. They don't have difficulties as much in an environment like this where they choose a seat because they know where to sit, where the situation is kind of static and there is only one person speaking, like in a classroom. They know how to handle that. The problem is when they are in the playground where so much is happening and people are moving and lots of children are talking, there they have difficulties. And also when they go on school trips. Imagine when you go on a school trip, you are in a museum, the acoustic is bad, all children are running around. And so those are the situations where they could use a better training of specifically where to place themselves and how to learn how to identify sounds. So for that, we created, the project is called Lyt again, which means listen again in Danish. And we created, so again, we are a small lab. So you cannot expect from us exciting graphics or also exciting. So this is what we could do to help these children with the capabilities that we had. And so, no less, the children enjoyed. We had a music museum where you go around to listen to the instruments. You need to find the right instrument. In that way, you learn about timbre. Or in the playground, so there was this treasure hunt where I think from the picture you get the point. In the treasure hunt, where you have lots of boxes, each box has a specific sound object, and you go around, you need to find different sound objects. And so what we found out in this project is that, first of all, so this is just some screenshot from the... So we recruited 22 children, and we asked them to take this up and take it home for 3 months and play this game. And then we were looking at if they were getting better in spatial awareness. So after every month, we were calling them for a focus group, or the people from the hospital were calling them for a focus group. And then we were discussing how this app was helping them. So they get better, but again, we are not game developers. So 3 months for these games was too much for them. So a couple of months would have been already enough. And also, another issue is, so how do we know? So everybody was delivered the same kind of spatial sound. So they were more training to understand that it is important to place yourself in a specific place in order to hear what you want to hear. But we don't know if the quality of the spatial sound experience was precise enough, because it should have been specifically created for each hearing impairment in order to be precise. And also, but at the same time, so for example, there was an acoustician involved in the project who was suggesting to create a very, very precise auditory simulation of the specific music museum, and they record the characteristics of each cochlear implant. So that would have been a project of 5 years, and if that was the case. So there is, again, a trade-off between how precise do you need to be and how accurate. So in this case, we were not very precise, but we achieved the goal to make them more aware of spatial issues and how to use virtual reality to train, but still it cannot be considered as a precise training tool, I would say. So again, the issue of accuracies versus complexity versus also responsiveness, because of course we were wanting to use the MetaQuest because it's very easy to give home and super easy, again, usability. The children could set it up themselves and play with it. But of course, it doesn't have an external computer. So also the computational power for the audio-visual rendering was also something to take into consideration. And so moving a little bit on the other side of the continuum in augmented reality. What are the issues in augmented reality? Of course, for spatial simulation, we also need to take into consideration the acoustics of the physical world. And there is a very nice technique, efficient simulation of augmented reality. Oh, well, that was the scattering delay network was proposed by Enzo De Sena, and we adapted it to augmented reality. It is a very efficient but rather accurate way of simulating spatial sound. At the beginning it was not for virtual reality, but now it's used a lot also for virtual and augmented reality application. But again, something that it is more crucial in augmented reality is what Werner and colleagues define the room divergence effect. So how far can the acoustics that you're simulating be from your idea of the acoustics of the real space in order to be considered as plausible? So basically, the question is, how much discrepancy can we have in the acoustic simulation of how one considers the real world should be or how the real world looks in order to make this experience accepted as plausible. And this, I don't think we still have an answer. So, to this question, how much audiovisual discrepancy can we tolerate? And again, it depends a lot on the context. I can give you a context where it was totally intolerable. This is a project that we did. It's called Holoband. It's also to train individuals with hearing impairment. But in this case, it was an older musician who had lost most of his hearing. And the idea, I'm going to show you a video. So the idea was to help reacquire his ability to play music in a band. So again, as I said before, individuals with hearing loss are pretty good in one-to-one, but then when we have conversations with multiple people or music with multiple musicians, it tends to become combined all together. So they don't hear the individual instruments, but they can get it all blurred, and that, of course, reduces the appreciation of playing or going to concerts. So this is another case where augmented reality could help. Again, audiovisual integration. So placing augmented musicians in specific places where each instrument is. And then in this case, we noticed that many elderly individuals, they prefer augmented reality than visual reality because they don't want to be completely obstructed from the physical world. So this is why we decided to use the HoloLens. And I want to show you a small video of what the person, this is a person trying the experience. So now this, in the HoloLens, these augmented characters appear, and they appear where the where the sound of the instrument is. The doctor here with a tablet can move around the instrument so the person can associate the instrument to the musical, so the image of the instrument to the sound of the instrument, and again train how different instruments sound. The problem with the HoloLens is that calibration was really kind of a nightmare, I have to say. So many times the experience was really dislocated in space. So of course, again, how much audiovisual intolerance can we tolerate? In this case, it was really disturbing. It was too much dislocated, and it didn't really work. So it required too much extensive calibration. It was not really plug and play to have it suitable for this experience. So, and again, in this case, also the ventriloquism effect, not always this capture of audio thanks to vision was happening. And if it doesn't happen, of course, the point is completely missed. So I showed you experiences created in 3D. Of course, it is to create a more realistic situation. It's also possible to use 360 cameras. And we had the pleasure of recording the Danish National Children Choir singing. They created a specific rehearsal for us. In this case, the idea was for children who have anxiety to go to sing in a choir. In Denmark, singing in a choir is a very, very popular activity. But unfortunately, there are some children with social anxiety who cannot go to physical choir. So we created for them a virtual choir. This virtual choir was achieved by recording the physical choir with, in this case, we use very simple equipment. So just Ambio, which is first order ambisonic, and the Insta360 Pro camera. Why did we do this? Because we could have used a Eigenmic or a more complex setup to have a much better experience, right? Also, it would have been really worth with such a beautiful choir. But it was not the purpose of the application. So I can show you the purpose was for children to experience this virtual setup. and be exposed to a virtual choir. So I'm going to show you quickly what. I think the sound is not. I'm not going to sing for you. So should I go back to the
system settings?
So I go here. It's ID4, so that's what they told me.
Yeah.
Yeah, could you? Yes, here it is. Thank you. Yeah. So as you can see here, the child is looking at the choir, and by being exposed to the virtual choir, then the children that then participated to the experiment, some of them actually, they accepted to go to sing with their own class. And as you can see there, those children that usually are by themselves and not really moving and so on, the fact that they were not in the physical world made them more open. So it's a nice application of also spatial sound to help individuals with specific needs. And again, so here we were thinking about content versus technology. In this case, it was much more important for us to have a content that was appreciated by the children from the visual point of view. So it was very important to capture the essence of being in a choir than having a very high fidelity, like with a 60 microphone, 60, yeah, with an eigen mic, which could have given us higher order ambisonics, but the child would not have cared about it, let's say. So, and in terms of accessibility also, that was becoming very important during the pandemic. What I mean here is that we were running some concerts. So this is the Ambisonic Concert Hall at the Royal Danish Academy of Music. So they have a very nice ambisonic system with 48 speakers, but of course everything was closed. So one of the applications of audiovisual spatial audio is to recreate these spaces in virtual reality. So a composer or a person who has to then use the physical space can test their music, can test the application in the virtual space before taking it to the real space. So in this case, well, you can see here I hated this sound, so here maybe. But so, yes, this if you want, you can listen to it. It's a binaural rendering, so you can listen to it afterwards. But the idea is can we create physical spaces? How can we bring them to virtual spaces so people can use it and they become more accessible to a larger audience? So my timing maybe is a little bit running, so we can, thank you, yes. So I would like to discuss with you some of the challenges that using these technologies bring, and also so we can have a little bit of time for questions. So as you could see from the viewpoint of auditory displays, we have so many possibilities nowadays, so many technologies and so much software available. So one of the questions is, well, first of all, how can individuals that don't have access to more interesting spaces with the loudspeaker, how can they have access to that? And also from the point of view of the software, how can one choose which kind of software to use? There are so many possibilities. But one of the issues that I discussed also before is as a computer programmer or as engineers, maybe we can try to make our software, if we want people to actually use it, we can think a little bit more about the user interface and the usability of the software we provide. Because many times, like for example, we're talking about HRTF, many times we just provide a MATLAB script. And a poor human being, how can they use this if they want to create their own HRTF? So this is, again, if we want to make it more accessible, some they just like to make the software for themselves, and that is totally fine. Also, something that I think is still a very big challenge is how to create this sense of co-presence. So, unfortunately, I could not go to the concert yesterday, but these networked sound experiences, they are still extremely challenges. I experienced only one, actually, at the conservatory in Copenhagen. They have this very sophisticated LoLa system, which is developed at the University of Trieste, and it has a very high bandwidth, and it has been developed for like more than 20 years to create mostly learning, distance learning. And that, I think, is the only time where I could experience that the audience that was from the other side, I could feel like they were in the same space as me. Also, the spatial sound experience was extremely well designed. Otherwise, I think so many times we still feel like this barrier. And not talking about only concerts, of course, also communication. There is still, I mean, these Zoom talks is not at all like being here in a real world. So what makes that sense of co-presence? What does it make us feel? There are so many elements. And it's not, of course, just the technology. It's also the human factor. And so this network concert experience or networked experiences, they are still, I think they're one of the big challenges, because if you are alone with a virtual reality display, you kind of feel like you're there, or you can make it feel like you're there. But these shared experiences, they still have so many challenges, I think. Also, I mentioned about we have been working with elderly and with children, and they require completely different tools, completely different attention, and completely different approaches. So you cannot ask a child or an elderly, for that case, to sit for 3 hours in an anechoic room and listen to beeps. That's not human to do. So, but at the same time, how can we do some experiments which are not only some qualitative observations? So how can we actually obtain data that are meaningful without torturing the population? And also, how can we design? So I think Microsoft has a very nice, for audio, so we need to think about, there are individuals that are hearing impaired. You can also not be hearing impaired, but get a ear infection. So then your HRTF is going to be all messed up. Bartender, I'm not sure. I think it's the cocktail party, what they mean. So situation where many speakers are there. And speaking of that, I was looking a little bit about the proceedings. And well, I can say as a disclaimer that we are running in a couple of weeks this Digital Audio Effects Conference, and the situation is way worse. There are almost no user studies at all. But also in this conference, I was looking only at the category 1 paper, sorry, I didn't have the time to analyze in depth the others. Also, among the 26 papers, maybe some have been declassed to category 2, because in the first, in the presentation that Franz made, there were 17. Anyway, among the 26 papers that I saw, so 15 they didn't have any user studies, and almost all the others, everybody was a male engineer with a couple of female, and it was always from the company or from the students. And sometimes, of course, it makes sense to have expert listening. It depends a lot on the context. But sometimes we could think also of expand, because then we get maybe more interesting results. Of course, it's not easy. It's challenging to go outside the lab, and it's very hard to find people that have the time or the possibilities to come and do your test. We are all in the same boat. So also, we have been working a lot in designing these experiences with the population in mind, because we are not the children. We are not, in this case, these are the children with hearing impairment. And even doing so, they found our games boring. So it needs always more iteration, and they should be involved from the beginning and through the whole process. And also, speaking of what we mentioned before, how can we have proper measurements? So in a very nice book by Sorenbeck, and it's a bit dated now, but they have a nice book on perceptual audio evaluation, where so there are three elements. We know pretty well how to measure the physical parameters. Also, perceptual studies are pretty well established now. But what about presence, immersion, all these very cognitive and high emotional and higher level phenomena? Those are still very hard to design for and very hard to measure, and also very hard to define. So everybody's talking about them in a different ways depending on the domain. And I think this paper by Jenny, Claudia, and co-authors, I think they have a very good point. That now they're talking about VR audio. But it's true, we are still measuring localization and kind of basic parameters. But also, we don't really look at how different researchers approach. So there is not a general, there are no general guidelines, and also we are still not there in understanding more higher level phenomena. So there is still really a lot of work to do in that sense. And since the theme of the conference is spatial and immersive audio, I was also thinking, maybe something that you can think about, is all spatial audio immersive, and is all immersive audio spatial? And again, I think it is really important that we approach these issues from a different perspective. So this I'm just pointing out to some, there is much more. Societal perception, perspective, technological perspective, there is really a lot. But the user experience perspective, perspective. So there are lots of things that, and this is why multidisciplinary collaborations are very important, because none of us can do it all. So I would say that here we are mostly here, and also a little bit here in the perceptual side, but everything else is not something that we can do on our own. We need to find good collaborators that help us tackle these problems. So just a little promotion of this open access book that Michele Geronazzo and myself co-authored, co-edited last year. So it's open to everybody, and it addresses both technology and application of sonic interactions. And if you want to talk about sonic interaction more, I will be around every day. And thank you very much.
Thank you very much, Stefania. Thank you. It's great to see all the research you're conducting to make spatial audio more accessible to everybody. It's really inspiring to see your keynote speech. So now we invite you to ask questions. So please step forward. There are 2 microphones in the in this way. So please step forward, and you can queue up if you want.
Thank you, Stefania. That was great.
Thank you.
Yeah, just curious with the whole HRTF thing. Considering there's so many applications, right? Do you feel that is there certain applications of HRTFs that work, or are the current solutions in HRTF working better for certain applications than others, or where is the HRTFs and which applications are they failing the most? Do you have any intuition? I mean, it seems to me, for example, like
so where they are useful, you mean?
Yeah, no, where they work best, because like there's so far we have some solutions, but I think they work for some things, but they don't work for others.
But you mean the personalized, or?
Let's say it's personalized, like the best kind of solution that you can think for HRTF. So individualized, measured, or so forth.
I mean, the personalized, I think they work very well in an environment where there is no visual cues, where you sit and where you're really concentrated on listening, and then you can pinpoint where the sound is, and then you have a very precise experience.
But is there like a specific, like let's say, application where it doesn't work at all that you think that's kind of like this is where it should be? Does that make any sense? I will ask you then. I will ask you later on, so no worries. But thank you.
Really enjoyed it. I was wondering about this universal HRTF you mentioned. That sounds interesting.
Oh, is there anybody from Meta here? So I was just reading about that, and what I understood, I didn't find a scientific paper. I found in the documentation of the Meta Audio Toolkit that there has been, it came out in July, so it's very new. And what I understand, if somebody is here, I'm sorry. So they measured, so they invested a lot on audio, so they recorded personalized HRTF of different individuals. And if you were at the AES Harvard conference last year, actually many of the participants got their HRTF measured. I don't know what happened to that, but the idea is that then with this new database, they could create a better model of what a general person HRTF should be like, which is not the classic ones used before. And they measured the difference between the new one, generalized, versus the universal, which is also generalized, but it's just to call it different. And then they saw that it performs better. Significantly better.
I just had a small question. Some of the work you're doing in multi-user virtual reality music things, how are you looking at networking this? What sort of infrastructures are you working with in terms of technology in developing and deploying these multi-user experiences?
Yeah, so for us, what is very important now is to take the technologies outside the lab, so to take it to the hospital or to the schools. So we really like, in terms of display, we really like actually the Meta Quest, because it's very portable, and then so there are some available network solutions. For our applications, the latency is not significant. But we didn't do like jamming in virtual reality with, so all the experiences are quite, they don't require a very high, high fidelity, let's say, networked experience. So
okay, so it's mostly sort of single user experiences that you're focusing on then, where it's playback rather than real time between multiple users?
Well, when we were working with multiple users, in that case, it was autistic children which were playing virtual musical instruments together for exposure therapy. So in that case, they had some, they were playing with the controllers, either with actually hand-tracked or with the controllers coming with the hand-mounted display. And then we had like 5 children. And the important thing was, of course, that there was no disruption of so that the connections were solid, so they didn't experience any breaking of the.
Yeah, I get. I'll send it over.
I'm around. Yeah.
Hi, Remy here. I was going to respond on the Universal HRTF.
Oh, thank you.
My team, released that toolkit. It's basically a regular HRTF. It was measured in our lab, and there was a lot of subjective testing and perceptual studies that went into selecting the HRTF, showing improvement in things like elevation perception, for instance, for most people. It's still a generic HRTF, so it's not personalized. I believe the previous one that had been used for years in this Oculus Spatializer was based on the CIPIC database, so this now is based on our own measurement in our lab. But happy if anyone has questions to talk afterwards.
Thank you.
Okay, hi Stefania.
Hi.
To stay on the topic of HRTFs,
of course.
we have discussed that before. I liked the answer you gave to the first question about this, because if you sit still, then this might make a difference. I haven't seen it proven, but it might from other. If you have fast tracking with 6 degrees of freedom and moving around, I think it has been shown that the right generalized HRTFs work as good as it can be, top of the plausibility direction. So that's really where we are in the moment there. And you can listen to it over there.
Thank you.
Thanks. Maybe my question was slightly answered by that, but plausibility versus accuracy in AR feels like the big question. Matching the room reverberation, the divergence effect you spoke about seems the big obvious thing to get right. After that, what's the most important thing that we need to reproduce to create a plausible virtual source in augmented reality?
Oh, well, in augmented reality, the main challenge is that we also see the physical world, right? So you have the acoustics of the physical world, which is combined with the acoustics of the augmented world. So it's not like in virtual reality that you're completely occluded and you can provide just the virtual world. So these two, they need to match, and also so you need to take into account both of them, and they need to be both plausible, basically, and plausible individually and together.
So say we nailed the reverberation, what other aspects of reproducing that virtual sound source do we need to get right? Say source directivity or using individual...
Yeah, or self-sounds. So you're moving around, you're doing things. In the real world, when you move around, you make sounds, footsteps or anything. So all the sounds that you produce as an individual, or the interactive sound that you produce. So if you hit a wall, you will make a sound, and it has to...
Yeah, great. Thank you.
I have a quick question related to Jake's question, actually. So, yeah, room incongruence issue, and this is really important to resolve to have a plausibility. But how important is visual cue compared to auditory cue? For example, if you see something right there, then, well, we don't have to have very accurate rendering, perhaps, because you see things, and in real life, I mean, even without using binaural technology, in real life, we are very poor in localizing sound without visual cues. So what's your view on that, the relative importance between auditory and visual?
Oh, for localization?
Yeah, in VR situation, yeah.
Oh, definitely, because we are much better with our eyes than with our ears to localize where a sound is from or how far it is. So seeing an object, it really, really helps a lot.
How about the overall immersive experience, like, you know, sense of being there at a higher level? You know?
So it depends. The visual, so it depends also if it is a space alone or if it is a space with other individuals, because that becomes really complex when there are also avatars and so many. That is really very challenging still. But if it is the space alone, I think we are able to reproduce it.
We have a lot of recording engineers in this room, I know, and you know, when we play 3D recording in a playback room, sometimes you close your eyes and just try to feel the space, you know.
Exactly.
And then sometimes you open your eyes and then that illusion is broken. And I think it really depends on the context, the importance of visual cue, I think. In VR, you always have the visual cues with you, so it can help you localize sounds and everything. But I think it's sometimes more challenging without visual cue, and you feel immersed. It's very challenging task we found in general. So I'm sure you can experience a lot of demos in this conference. But yeah, any other questions? Just one more. We have 2 more minutes. No, actually 1 minute. So any more question? Okay, if not, thank you very much, Stefania. So this concludes our first keynote session, and we have 15 minutes break before the paper session starts in this room. Thank you. Enjoy your coffee.